presently working at Netsim. Today I will be demonstrating Netsim network simulator with a focus on cognitive radio and the various features and functionalities the scientific tool provides. This Netsim allows user to design, analyze performance, validate networks, and it also permits the researcher or the user to edit the network protocols. So, hello Shravan, can you just mute the...
Okay. Now it's muted, you can start.
Okay, fine. So why Netsim or any network simulator? So with the advancement of technology, newer protocols are being introduced very frequently, and it is very difficult to keep oneself updated with the latest happenings. Furthermore, analyzing a network behavior using traditional analytical methods or rules of thumb has become really cumbersome, and it is not easy to manually analyze the network behavior, considering the fact the large number of parameters involved. Hence, Netsim is used to provide an accurate understanding of network behavior and the associated problems and possible solutions. So, Netsim is a scientific tool for designing and validating networks and protocols, and hence has a lot of relevance in protocol research and development, and in defense, for instance, in simulating network-centric warfare. The wide range of technologies possible to simulate in Netsim are internetworks, which is LAN, WAN, wireless LAN, then mobile ad hoc networks, WiMAX, cellular networks, which consists of GSM and CDMA, then cognitive radio networks, LTE, and wireless sensor networks. In Netsim standard version, users are also provided with the C source code of the network protocols implemented, and they are based on the IEEE and IETF standards. The purpose of providing this C source code is to enable the researchers to edit the standard protocol code and implement it according to one's own design, then link it with Netsim and analyze the performance of this newly designed protocol. So Netsim has a huge number of customers, varying from industries where it is used for network design and validation to defense labs, where it is used for network-centric warfare simulation. It is also used in R&D labs for protocol development, new technology testing, and many PhD research papers are also published by utilizing this tool. Netsim also has an academic version to be used in network labs of undergraduate curriculum and advanced network labs of graduate courses in electronics, computer science, and other domains. So, providing a holistic view of Netsim, users will design the network and configure it in a graphical user interface, which is just click and drop, and this will be simulated by the Netsim engine, and thereby, as a result, it will provide multiple metrics regarding the performance of the network. User need not require to write any script or code while designing and configuring the network scenario. Now, one striking feature of Netsim is this Netsim engine itself. So as you can see, it is utilizing a virtual network stack, which actually copies the real-world TCP/IP stack, and hence it makes it very easy for any user to edit the protocols and get fairly accurate result. It also enables the user to perform research on cross-layer protocols like, let's say, Leech. So Netsim is divided into component or libraries. The standard version users can make a selective choice while using Netsim. This is the list of libraries, or as the contents of each libraries and the corresponding IEEE and IETF standards referred during implementation. For illustration, let's say component 1. So it consists of wireless protocols and wired protocols like WAN, LAN, wireless LAN. And the implemented international standards, as you can see, IEEE 802.3.11, ABG and AC. Similarly, component 2, it consists of network based on legacy technologies. Component 3 is based on BGP. Component 4 contains wireless ad hoc networks, and like mobile ad hoc network and WiMAX. Component 5 consists of cellular networks like GSM, CDMA. Wireless sensor network and personal area networks, they belong to component 6. Component 7, a library, contains cognitive radio networks. Component 8 contains LTE. And finally, component 9 contains military radio, which is usually provided only to customers, enterprise customers. Now, in Netsim V8, we have added newer protocols like LTE and revamped old protocols like BGP and cellular. Furthermore, new features like dynamic metrics, the user interface property view editing, and new application models like peer-to-peer, HTTP email has also been added. So I will be dividing this demonstration into two sections. The first part, I'll be explaining how to design and analyze networks in Netsim. And in the part 2 or second part, I will show you how to edit the cognitive radio protocol source code and link it with Netsim. So to create or simulate a network scenario in Netsim, users need to go to the cognitive radio networks technology. Now, before proceeding with the simulation, I would like to go through the basics of cognitive radio, and then I'll be implementing it in Netsim and showing you all the features and possible parameters you can set in Netsim. So the cognitive radio networks works on the IEEE standard, that is IEEE 802.2 wireless regional area network. And the reason why cognitive radio came into prominence is, as you can see in this diagram, this is actually the frequency allocation diagram. And in the year 2002 in US, the spectrums were allocated according to their purpose. The problem was there was no unused spectrum, or extra spectrum was not kept empty for allocation in future to newer technologies. On the other hand, the technologies which were allocated the specific spectrum, it has been noticed that the usage is continuously growing. Let's say, as you can see here, the Cisco forecast for the mobile data traffic till 2019. As you can see in 2014, the amount of exabytes per month is only 2.5. But by 2019, it is expected to be around 24.3 exabytes. From here, you can easily understand the allocated spectrum for mobile data traffic is not enough. So this, in turn, will lead to spectrum crunch. So spectrum crunch refers to the lack of sufficient wireless frequency spectrum required for the communication among the growing number of consumer devices. Now, after this allocation of spectrum, in the year 2005, a report was published by Shared Spectrum Company and Illinois Institute of Technology. So the goal of this paper was actually to gain a better understanding of the actual utilization of the spectrum and to identify the spectrum bands with low occupancy. So from the report, it was noticed that even though spectrum was allocated, most of the spectrums were inefficiently used. For example, here you can see the TV bands. Hardly 25% was used. And hence, this results in what I would say is a spectrum hole, that for some time the spectrum is being used and the rest of the time it is not used. So whenever the spectrum is not used, these regions are called spectrum hole. I'll be going more into this in details later. So from the report, we can see that the spectrum measurement indicates there is a heavy spectrum utilization in unlicensed bands like ISM band. but the spectrum utilization in licensed bands like the TV bands or the cellular bands is relatively low. So to avoid this discrepancy, the cognitive radio technology is a promising technology for efficient utilization of all the available spectrums. So what is cognitive radio? Hence, cognitive radio is a wireless communication system, and it has two important properties. The one is it has to be aware of the environment and its changes, and accordingly it should adapt its transmission parameters. To be more specific, it needs to be having cognitive capability. Cognitive capability means the ability to sense the unused spectrum in the environment at that specific time and location. And the second point is the reconfigurability, that is, receive and transmit the different frequency bands and accordingly reconfigure its parameters to select the best band. Also, as per the IEEE 802.22 protocol, the operating frequency for cognitive radio should be within 54 MHz to 862 MHz, which is actually the TV band. So as said, why cognitive radio? For like improving the efficient spectrum utilization, as the current wireless networks are regulated by fixed spectrum assignment policy, and hence cognitive radio is a new paradigm to provide the capability to share or use this fixed spectrum in an opportunistic manner. And cognitive radio is a wireless regional area network, so you can understand from this diagram that it will work from around like till 30 kilometers and a few more. So in cognitive radio, there are basically two kinds of users. One is primary user and one is secondary user. And this is important because primary users are the license owners and they have the permission to operate in this certain spectrum bands. Secondary users, they don't have any license band assigned to them, and hence they are required to utilize the primary users spectrum in an opportunistic manner. And for each of the users, they have their respective base stations to control the access of the spectrum. And as per the standard, the physical layer is designed to support the vacant TV channels, that is the 54 MHz to 862 MHz, and provide a wireless communication distance up to radius of 30 kilometers. And as per this specification, it is based on the OFDMA. So, to break down the functionalities of a cognitive radio network, one can say that it has four main purposes or the four main steps while performing the. So the four main steps are, one is the spectrum sensing. So the first step is the cognitive radio user should have the ability to sense the unused spectrum at any time and location. And then comes the spectrum management. So after sensing the spectrum, if it finds that the spectrum is idle and not used, then it has to check whether the policies permit it or not. So based on the internal and external policies, the allocation of channel is done. And also the spectrum availability is also important. This third step is the spectrum mobility. So let's say the primary user is not using the channel and the secondary user is now utilizing it. After some time, when the primary user returns, the cognitive radio user must vacate that spectrum and move to some other best available spectrum band. And spectrum sharing, in case of multiple secondary users, the cognitive radio network must provide a optimal spectrum allocation method so that multiple secondary users can equally share the spectrum. So this is the CR cycle, cognitive radio cycle. So you can see here, first the spectrum is sensed, the medium is sensed to detect the unused spectrum channels, and then the spectrum decision is considered, that whether the best available, whichever is the best available spectrum, use it and transmit data. In case if any primary user is detected, so using the spectrum mobility, they will have to hop into some other spectrum. And in case if there is multiple cognitive radio users, secondary users, they need to share the spectrum. And this is the cycle. So as usual in Netsim, this is the base station, and the CRCPE constitutes the secondary users. For primary users, we have the incumbent. So in Netsim, the primary base station and the secondary base stations both are the same one. So this incumbent is the primary user, CRCPs are the secondary user. Now to set their parameters, now for setting up the primary user parameters, the user can specify the operating frequency start, the operating frequency end, that is the channel which is allocated to the primary user, and the operational time, how long is the primary user operational in that channel, and for how long it is not operational. Along with that, the geographical area. So it, by the keep out distance, it means that the influence of this primary user on this channel is having a 100-meter radius. So this is all about the primary user properties which the user can set. And then, being a secondary base station also, the user can, or the researcher can specify the amount of spectrum allocated for the secondary users. That is, the secondary users can scan which channels are free within the maximum and minimum frequency. That is, if I set, let's say 90, so the secondary users have the ability to scan the channel from 54 to 90 and find the free spectrum within this. And as per the standard, the channel bandwidths are 6, 7, 4, 8 in cognitive radio. So this is all about the devices. Users can further attach a wired backbone. It's a communication between the CR network and the server. So users can communicate from wired node to CRCP or CRCP to CRCP. So this was all about the devices. Now how the cognitive radio works. So as you can see here, the time has been divided into super frames. So again, one super frame is of a duration of 160 milliseconds, and each super frame is again divided further into 16 frames, each of 10 milliseconds. Furthermore, each super frame has a super frame preamble, and each frame has a frame preamble. It is mainly used for synchronization, and in the starting of the super frame, there will be a super frame control header. So the main purpose is to carry the base station MAC address and also details about the quiet periods for sensing and other information. So the way it works is, as I said just now, whenever a new super frame is going to be transmitted, the base station transmits a super frame preamble and then a super frame control header on the operating channel. So the super frame control header is very important for the secondary users to establish communication with the base station. Now, as I've said, each super frame again consists of 16 frames. Now let us go in detail to see the contents of each frame. So in each frame, two operations are mainly performed. One is the downstream and the upstream. So as you can see here, the downstream subframe and the upstream subframe. So during the downstream subframe, the data is transmitted. I'll be going to this in details when I'll be showing you the packet trace. So the thing which I want to show you is here that you can see the packets like FCH, frame control header, the DS map, the US map, UCD, DCD. So all these control frames we can also see in Netsim that is being transmitted. So let's go. So let me transmit data from CRCP-B to CRCP-C. So as you can see here, the device ID is 2 and 3. So accordingly, I have set it in Netsim also. And users can further change the various packet size, the values, the interarrival time, how frequently packets will be generated. And if they want, they can even put email kind of data, video, voice, HTTP, database, FTP. So all these options are available. I am using just a basic scenario. So by the time the simulation ends, I would just like to go through this detail of the frame structure. So what actually happens is after the transmission of frame control header, the DS map and US maps, they broadcast messages that specify the source allocation in the downstream and the upstream frames. Then you can see the UCD and DCD packets. They are usually transmitted by the base station at like periodic intervals to define the characteristics of the downstream and the upstream physical channels respectively. And then in between the downstream frame and the upstream frame, you can see the TTG. So it is actually the transmit receive turnaround gap, and it allows the secondary user to switch between the receive mode and transmit mode. So what happens in downstream frame is the data is obtained by the secondary user from the base station, and in the upstream frame the data is transmitted from the secondary user to the base station. So yes, so the simulation has ended. So if I go and view the packet animation, so as the routers are here, you can see the routers are creating the routing table by sending the OSPF LSA packets. OSPF protocol is running among the routers. So you can see just now the SCH packet was sent, and after that the FCH, that is frame control header, then DS map, then the US map, then UCD packet, and then DCD packet. So as I have said, they are specifying the resource allocations and the physical characteristics of the channel to the secondary users. So this will continuously go until and unless there is any packet to send. So actually the first packet will be generated after around 1460 microseconds. So now as you can see, TCP protocol was enabled. So after the bandwidth request, BW request, it is now sending a TCP sync packet. and the packet is now forwarded from the base station to the destination. So again, as you had just now noticed, the bandwidth request was sent to the base station. And syncac. So I'll just increase the time. Okay, so you can see here CBR152 packet is being sent, and the packet is actually segmented, so you can see multiple times the same packet is transmitted, and for each of them a TCP acknowledgement is also transmitted. So for every frame, this frame control header, DS map, US map, UCD, DCD are getting transmitted. So this is more of like a packet animation view, and the other analysis features which the user can use for cognitive radio network is, you can see here, the network metrics. It allows the user to view the values of the metrics obtained based on the overall network. Then the link metrics. So it will display the values of the metrics pertaining to each link, like packets transmitted, packets errored, and collided, and the others. The queue metrics, it displays the value of the queue metrics for the devices containing buffer queues like the router, the access point. Then we have the protocol based metrics. So as TCP is running, the user can see the TCP connections, the number of segments transmitted, retransmitted, and so on. Then this is the IP based metrics. Then the various IP forwarding table present in each of the nodes. And as OSPF protocol is running in the routers, so you can also see here the routing tables. And then the ARP matrix, ARP table. Now, one application is running, that is from CRCP-B to CRCP-C. So details related to the application are displayed here. So how many packets were in total transmitted and how many packets were received. In that terms, what was the throughput and the average delay in the network. Now, as you can see these protocols, as you can see these parameters, these are based on the cognitive radio. So the cognitive radio base station metrics, where it displays how many superframe control headers, the frame control headers have been sent. Then the user can see the CRCP based metrics, how many superframe control headers are received and the frame control headers are received. And this is the primary user base details, like what is the frequency the primary user is using and how long it is operational, how much time it is idle. And this is the channel based metrics. So the 54 to 60 megahertz frequency, how much is the spectral efficiency, that is how much is being used by the secondary user. So this is, all these details are actually known as performance metrics. And the packet animation view. So these two features are present in both standard and academic version of users. But for standard version users, which is mainly the researchers, they need more analysis techniques to understand the protocol in depth or the working of the network in depth. So we have packet trace, event trace, and the dynamic metrics. So Netsim allows users to generate these trace files which provide detailed packet information useful for performance validation, statistical analysis, and also custom code debugging. So the packet trace, it logs a set of the chosen parameters for every packet as it flows through the network, such as the arrival time, queuing time, payload, overhead, errors, collision. And the event trace records every single event along with the associated information such as the timestamp, event ID, event type. And the dynamic metrics, it generates a throughput graph through the link or for the application, and if TCP is running, the user can also see the congestion window. The advantage of dynamic metrics is it allows the user to monitor these parameters over the simulation time. And hence it helps the researchers to understand the behavior of a network at any instant of simulation time. So we will be now analyzing each of these analysis features exclusively for standard version in depth. So by the time the simulation finishes, let me continue. So in cognitive radio, a channel has various status. So when the channel is specified as protected, it means the WLAN operation has been detected. The operating means that the channel is currently in use. A backup channel is that which is cleared to become the operating channel. That is, a secondary user can use it. And candidate channels are those channels which are now not being utilized but can be utilized further in future. So they are the candidate channels to become a backup channel. And some of the channels are considered as disallowed. That is, as per the regulatory, internal, external policies and regulatory constraints, these channels cannot be used by the secondary users. And the channels which are not yet sensed are considered as unclassified. So as I was discussing the analysis features exclusively for standard version. So let me open packet trace. So as I had said before, the packet trace will log the details of each packet transmitted. So you can see here. So initially, the router is transmitting OSPF packets to create the the routing tables. And then the cognitive radio is transmitting, that is the base station is transmitting the superframe control headers. So the superframe control headers is being transmitted by the base station to node 2 and node 3. That is the two secondary devices, 2 and 3. And after transmitting the superframe control header, the frame control header is transmitted, then the DS map, the US map, the UCD, the DCD, and the rest packet. So it continuously goes on. Now, if we check for each packet, the details we get is the source ID, destination ID, transmitter receiver, and also the application layer arrival time, the network layer, transport layer, MAC layer arrival times, and these all times are in terms of microseconds. Then whether the packet is successful or not, or did it collide, or did the packet get errored, so all the details is logged here. Along with that, the packet sizes, that is the application layer payload, the network layer payload, the MAC layer payload, and so on. So as a TCP is running, so you can see the TCP connection getting established and the source port numbers, the destination port numbers, and the other details. So for each packet, all the details are logged and shown here. Now you may notice here that the number of for the 50-second simulation, it's around 97,000 lines of rows are there. So to further help the users can utilize the features of Microsoft Excel filter to see properties like, let's say I want to see only errored packets. So automatically you can see only one packet got errored while transmission. And if you want more details, you can also see, I want to know the packets which were transmitted by node 8. So you can see the packets which are only transmitted by node 8 were actually ICMP echo requests. And then you can easily filter from 97,000 lines to just around like some 15-20 lines. So analyzing the packet trace in Netsim is really easy. Now we'll be going for the event trace. So the event trace will log the events which are being performed one after the other. So you can see here initially the router packets are, the routing table is getting created using the OSPF hello, and how these packets are flowing through each of the layers in the TCP/IP stack. So transport layer, network layer, then MAC layer, then physical layer out, then again it's going to physical layer in. So after the routing tables are created, so users can see the events for the cognitive radio, like frame control header is being transmitted, then the DS map, the US map, and the sub events which are getting performed, like transmit DS burst, TCP DST receive segment, transmit DS burst, TCP send segment, and so on. So you can see here the transmit US burst, that the upstream and the downstream. So user can analyze how exactly the protocol is working for this specific network design. So as I just now explained, the analysis for the academic and standard version both is the performance metrics and the packet admission. But for standard version, the exclusive analysis features are the packet trace, event trace, and this is the dynamic metrics. So in dynamic metrics, a graph is displayed, so users can see the link 1 throughput with respect to the time. And also they can notice for the application and the TCP congestion window. So these are the features only in the standard version. Now, so now in the second part of this demonstration, I will show you how easy it is to edit the network protocol source code and link it with Netsim. So Netsim allows the user to edit the protocol source code, and these C source codes are provided along with this tool. Users can use third-party IDE like Visual Studio 2010 to edit and debug the protocol codes. So now I will be performing a minor editing in the source code. That is, I will edit the cognitive radio code and I'll reprogram this protocol to print hello world in the console. So what will happen is whenever I'll run cognitive radio, it will print me a hello world in the console window. So as you can see here, these are all the C source codes for the protocols like AODV, and ARP, ATM, cellular, cognitive radio, DSR. So let me go to cognitive radio. So in this boundary radio function, I go to the init function. So this init function is executed whenever the protocol is called the first time. So whenever I'll run contrib radio, the first thing it will do is it will print hello world in the console, and it will wait for there is a get character. It will wait for me until unless I press a button, it will not continue the simulation. So the three easy steps to edit the code and link is this. The step 1 is to edit the code, which I have done just now. Step 2 is build the DLL. So to building a DLL in Visual Studio is just right click rebuild, and Visual Studio will be building the DLL for me. So as you can see here, one succeeded. And the step 3 is to go copy this DLL and paste it in the bin folder. So now Netsim will read this sleep cognitive radio DLL, which is the modified DLL. So let me go and simulate. So as you can see here, the hello world is printed just before the running of the protocol. And then when I press any button, character I provide, it will start simulation. So this is it. This is the editing of the protocol source code in Netsim, and it is really easy. You need not worry about the tool. Rather, we suggest the researcher to spend more time on his or her own protocol. So while editing the code or writing a new code, Netsim provides a wide variety of APIs. For example, in order to create a packet or copy a packet, that is create a duplicate packet, the protocol developer need not write the code manually. We are already providing APIs like create packet, copy packet, then getting the device IP, then sorting the list, converting IP to string, and many more. So presently Netsim has over 300 plus customers across 15 countries. So ranging from enterprises to research institutes and domains. So another thing I would like to show you in Netsim is like for, let's say, I'll be showing you one sample of cognitive radio in Netsim. Let us consider for the primary user, I am allocating 54 to 60 megahertz, and it is continuously operational. And the secondary users, they have the minimum frequency of 54 megahertz and the maximum frequency till 90 megahertz that they can scan and utilize. So as expected, what will happen is initially it will try to use 54 to 60 megahertz, but as the channel is busy, it will try to hop to another channel. So let us check that. So now if we go to CR channel metrics, we can see here that initially it tried to use the 54 to 60 megahertz channel. It's getting almost 0002 spectral efficiency. But as this channel is being used by the primary user, it has tried to search for the next best spectrum which can be allocated. So it has jumped. You can see the spectral efficiencies for the other channels which are not being utilized by the primary user. So in this manner, you can add multiple incumbents, multiple secondary users, multiple applications, and if you want to edit your standard, the cognitive radio protocol, if you want to edit the spectrum sensing, the channel allocation techniques, you can go and edit the code and then check the implementation in Netsim. So all these features are possible. So my demonstration is finished. If you have any queries, you may ask.
Hello.
Hello?
Yeah, if you have any queries, you can ask us.
Hello?
Hello.
No queries, thank you.
You can also write your query in the question.
Hello?
Hello. Yes, ma'am.
Hello?
Yes, ma'am. Yes, ma'am.
No queries, thank you.
Yes, ma'am. Yes, ma'am. Do you have any query? Nilja, can you show some wireless sensor network to them? It is one query.
Wireless sensor network. Actually, yesterday only there was a demonstration on wireless sensor network.
They were not there yesterday. So.
No problem.
Just a small brief on wireless sensor.
Right.
Ma'am? Ma'am?
Is my voice audible?
Yeah, your voice is audible. You can continue.
Okay, there's a lot of disturbance actually.
Yeah.
Fine. So in wireless sensor networks, users can place the sensors, and as we know, in a wireless sensor network, we require a sync node. That is the PAN coordinator, which will control this network. Now the sensors will sense the agent. The agent is nothing but the object. Let's say a fire, and let's say these are fire sensors. So these sensors will sense the location of the agent and will send the information to the sync node. Now, a frequently asked question that what kind of sensor is this? So it depends upon the implementer. So if I want to implement a environment sensor or body sensor, so you can accordingly set the sensor parameters like the sensor range, how frequently it will sense, the transmitting current, the initial energy. If it has some kind of energy harvesting like solar cells or some techniques, Users can also provide that. Or if your sensors are main powered, you can also set that. And I'm not going into much details, but you can also change the CCA mode, the ET threshold, the transmitting current. So whatever sensor you want to implement, you can set the parameters accordingly. And you can configure this for each sensor. You can also configure them to be mobile. So the sensors will move. You can implement the random walk, random waypoint mobility models, and also file-based mobility. And in case of sync node, users can set the beacon enabled mode, beacon disabled mode. And if it is enabled, you can set the super frame order, the beacon order, then the battery life extension, the maximum minimum backoff exponent which are used in CSMA CA algorithm. You can even set the environment parameters, and over all of this, the users can also modify the code. If you go to ZigBee code, you can modify the codes for clear channel assessment, the path loss, receive power, the shadow loss, the slotted CSMC algorithm, the unslotted CSMC algorithm. If you want to make modification and check the performance, you can also do that in Netsim, in the standard version.
Yeah, Atul sir, do you have any query?
No, right now we joined this somewhat late time, and due
Okay.
to that we have no more questions.
Sir, there is one more session at 2 p.m. So if you want, you can join at 2 p.m. also.
Yes, we are supposed to join at 2 p.m. on sharp time.
Okay.
Sunny. Yes, I am very fine. If you want to listen about the net simulation, Netsim software demo, you come at 2 o'clock at my office.
Yeah, 2 o'clock also you can join, or if you have any query for right now, you can also ask us related to
Yes,
software
yes.
or anything else. Any other queries? If you do not have audio facility, you can write your query on the chat box or question box. Nirja, there is one query that how the nodes are grouped together related to multicast network.
In county video.
Related to multicast network.
No, presently if you want to implement a multicast, you have to use like multicast, but by default multicast is not supported in Netsim.
Okay.
But you can use multiple unicast and to recreate that scenario.
Okay. Any other queries? Vignesh sir, do you have any query? Your voice is not clear to me, sir. Yes, sir. You can write your query. वो बार-बार ऑफलाइन ऑफलाइन यूज कर रहा हूँ ऑफलाइन Hello, Sumati ma'am, can you hear me? Hello, all of you. Do you have any query? Should we end this presentation? Hello.
சவுண்ட் வர மாட்டேங்குது இங்கிட்ட ஏசி
Okay, so we end this presentation now. If you have any query, you can mail us further. Okay, Nizar, you can stop now. No query now.
Okay, thank you, Shravan.
Yep. Okay.